All righty, friends. How y'all doing? Good to see you guys again one more time here as we finish off this Unit 5A. All right, so we've been looking at exponential and logarithmic functions. And we've been playing primarily when the base was e. That's kind of what we've been kind of basing everything off of. But what if the base wasn't e? So for instance, what if we were dealing with any other base other than e? Now, we also spent a day looking at inverses, and one of the parts about inverses we looked at was that if we were to take the natural log of e to the x, since they're inverses, that actually equals x. We also, because they're inverses, if you plug it into the one into the other way, you get x. They're inverses, they undo each other. Well, we're going to use one of these relationships today. We're going to use this one. Since e and natural log undo each other and you're left with whatever's with, I could actually take this and rewrite this as e to the natural log of a to the x. They would undo each other. And if I were to take a look at it that way, I could say, well, a to the x equals e times x natural log of a. And right now you're probably going, well, what's the point? Well, what if I were to wanted to figure out the derivative of that a to the x? Like, oh, okay, so this is where we're going. It'd be the same thing as if I were to take the derivative of this other side. So e, and I'm going to rewrite it instead of putting x in front. Remember that natural log of a, that's just some number, right? That's just some number. So just a constant number times x. So if I wanted to figure out the derivative of a to the x, it'd be essentially figuring out the derivative of the other side. So we've already dealt with this before. Derivative of e function is e natural log of a to the x times the derivative of natural log of a times x. Well, natural log of a is just a constant number. So a constant number times x, the derivative of a constant number times x is just that constant number. Even though it's a natural log, it's just a constant number. Now, let's go back and kind of rewrite that a little bit here. I can put that x back in front again. And we're going to do just a little bit of math magic here. And got the x back in front of the natural log. Let's turn it back into our exponent. So we got natural log of a to the x times the natural log of a. And then again, e and the natural log, they cross each other off because they are inverses. They don't really cross each other off. They just undo each other. So we end up with the derivative of a to the x being a to the x times the natural log of a. And if we wanted to take it even a little bit further, just like we've dealt with before, we could actually say that the derivative of a to the f of x would be the same thing as a to the f of x times the derivative of the exponent times, oops, there we are, the derivative of the exponent times the natural log of a. So it's the same thing we did before with the e function. It's just now we're adding one little part, the natural log of a. And technically, we had it before. We could have wrote it before as the natural log of e, but natural log of e is 1. So it was one of those things, we didn't include it. It was there, but we didn't necessarily include it because, well, we didn't really need it. So we got a derivative of any exponential function now at this point in time. It'd be great to be able to have a derivative of any logarithmic function. So let's take a look then at just a basic, oops, let's not do that. Let's take a look at just a basic log function. So for instance, let's let y be equal to the log a of x. And we could use a change of base formula here. The reality is I don't know how many of you guys remember the change of base formula. That's fine if you don't. We'll go the long way to generate it. And I can take the log of both sides by any log I want. So let's use the natural log of a to the y. So we're going the long way by actually proving the change of base formula. So now the y is in front. I can put the y behind. I did not mean to put an equal sign there. So y times the natural log of a equals the natural log of x. And if we divide both sides by y, or by natural log of a, we get y equals the natural log of x times, or divided by, the natural log of a. So when we put the two parts together, we find out that the log a of x equals the natural log of x divided by the natural log of a. So that's just a change of base formula. In case any of you all didn't remember it, we went ahead and just did it longhand and improved. So that means then, if I want to go one step further, well, no, actually we'll start there. So what if we wanted to figure out the derivative of of log base a of x? And that'd be the same thing as taking the derivative of natural log of x divided by the natural log of a. And some of you guys might be going, ooh, quotient rule. Yeah, I'm not going to do a quotient rule. It's actually a lot more simpler than that. So log base a of x. What I'm going to do, though, is I'm going to rewrite the derivative on the other side to be this. Let's rewrite it as 1 over the natural log of a times the natural log of x. So if I wanted to find the derivative then of the log base a of x, that'd be the same thing as 1 over the natural log of a times 1 over x. There's your derivative. And again, if we take this a little bit further, we could actually get the general rule for any log. Now, friends, please understand, most likely you are not going to see this on your AP test. Every once in a while, I've seen them throw something on there. And so you need to be ready for it in case you see it. At the same time, though, if you go and pursue calculus in college, they're going to expect that you guys have seen what all these are. So it is good for you guys to know, have a general idea of these other exponents and logs, not just the ones with base e. Let's see, it's going to be actually a multiplication symbol. So if we were to do the general formula, it would be like this. So those are our general forms of any log or any exponential function. They don't have to be e anymore. They don't have to be a natural log or have to be e to the x. It can be anything. So this is going to be kind of what we're playing with here a little bit today. And we'll just do a little bit with it. We won't go crazy with it, but we'll do a little bit with it. So, let me write those equations up here, those derivatives up here, just so we have them. And we're going to go ahead and play with a couple of these today. So we have natural log of a times a to the f of x times f prime of x. So here's what I'm going to ask that you guys to do. I would like to know what is the derivative of each of these two functions. So the first one I'm going to give you is f of x equals 7 times 3x, or 7 to the 3x plus 5. And let's try f of x equals 8 raised to the x squared plus 3x plus tan x. Something really ugly, because it can be really ugly at this point in time. It doesn't matter. All right, so there's our exponent. All right, friends, go ahead and pause the video, and we will go, and then we will meet back and talk about it. All right, you guys are finishing up here. I'm just going to actually go ahead and rewrite our other derivative up here. After today, we will have one more day where we learn new derivatives. We will learn 6 derivatives. One more day of learning new integrals, and that is 3 of those. Then we are done learning integrals and derivatives the rest of the time, and the remainder of the year is just applying. Okay, so let's see if we can do this. First of all, here's my base. It's 7. So I'm going to start off here then with the natural log of 7. And once I've added that, now I just treat it like my e function. So write my regular function, and then multiply by the derivative of my exponent. Okay, so we start with the base. It's very similar to what we were dealing with before. It's just we're going to multiply that derivative by the natural log of the base. Then everything else was just like we did with it before when our base was e. So now it's 8 times, or 8 raised to the big ugly thing here. Holy wow. What was I thinking? Times by 2x plus 3 plus secant squared x. All right, well, let's have you guys try a couple more maybe that are dealing with logs. Let's try, how about this? F of x equals log base 3 of 4x minus 7. And let's try f of x equals log base 5 of the cube root of 2x plus 1. All right, friends, why don't you go ahead and pause the video. Let's see what you come up with. All right, let's see how you did. First up, 3 is my base, so I'm going to start off with 1 over the natural log of 3, and then everything else is the exact same. So the log of whatever I'm taking the log of, 4x minus 7 in the denominator, and multiply by 4 in the numerator. And we're done. On this one now, be careful. I would have actually gone ahead and rewrote it. And And by the way, I just realized my notation was bad because I said those were equal, and those are not equal. Let's fix it real quick. That was the derivative that we found. Equals 1 over the natural log of 3. There we go. That's a little bit better. But on this one, I do want to go ahead and rewrite it. I don't like the way it looks here with that cube root. So I am going to literally rewrite the whole thing, because then I can take that exponent and I can move it in front. So 1/3 log base 5, 2x plus 1. Now we're back to being something a little bit more straightforward and easier to deal with. So the derivative, I have 1/3 because there's a 1/3 out in front, and I'm going to multiply by 1 over the natural log of the base, so 1 over the natural log of 5. Remember, whenever you're dealing with those logs, it's always good to go ahead and rewrite it whenever possible to make it something easier for you to deal with. All right, so we got some derivatives in here. Would be great now, since we talked a little bit about derivatives, it'd be great to go ahead and talk about some integrals. Now, we're not necessarily going to be dealing with derivatives of other logs, but we want to deal with we're not going to deal with integrals of other base logs, but we are going to deal with, just briefly, the integral of other exponential functions. So if we use our idea of what we have up here, and we undo that derivative by integrating it, we find out that it ends up being 1 over the natural log of a times a to the x plus c. So we get a real nice and pretty little integral for us to use, and we are going to play with that one just a little bit here. So to begin with, let me see if I can't throw some out here for you. We're going to be dealing with 2 different integrals. Let's try 7, 3x plus 4. And we will go with cosine of 2x e sine of 2x dx. All right, let's see if we can play this a little bit here. Again, I see that my exponent's got some. So just like we were dealing with e to the x, we still make my exponent u. So none of that changes. We're still doing a lot of the same stuff here, friends. So I still got to get my differentials to match up. So 1/3 du equals dx. So that means that my integral here is 7 u times 1/3 du. And we are going to bump that 1/3 on the outside there real quick. Whoop, just like that. Somehow I decided to turn that green. That's kind of fun. There we are. Equals 7u du. And now it's just the same thing we did before. It's just we're adding a 1 over the natural log of the base in front of it. So 1/3 times 1 over natural log of the base of that exponent, which is 7, times 7 to the u plus c. And again, we plug it back in here. So 1/3 times 1 over the natural log of 7 times 7 to the 3x plus 4. plus c. All right, and just like we dealt with before, I would have rewrote this one, where I put my e in front here. Times cosine 2x dx. So u equals sine of 2x. Du equals cosine of 2x times 2. Got a little chain rule going on there. So we get our differentials to match up. So 1/2 du equals cosine of 2x dx. So that's not too bad. Again, all the same stuff we pretty much did before. It's just now we're going a little bit further and we have a u sub with it. And we also now have also changed the base. So e sub. Oh man, I just realized I made a mistake there, gang. Sorry about that. Let me fix it real quick. This is the same thing we were doing before. This didn't change anything. I wanted you to have 3 as that. Sorry about that. If you guys already did on yours, don't worry about it. Don't worry about changing it. But I wanted to show you what would happen with it again. Sorry about that, friends. All right, so we have 3 to the u times 1. Couple mistakes there. So 1/2 du. So the 1/2 is going to go in front. Also, I'm starting to look at it going, wait a second, it's just a u. We've done these already. They didn't need another day on that. Oh boy, friends, it happens. All right, so same thing as before, 1/2. 1 over the natural log of 3. If it was still e, that would have been 1 over the natural log of e, which is just 1, which is why it goes away. 3u plus c. So we have our final integral here. Times 1 over the natural log of 3. Times 3 to the, oh, what was our u again? It was sine of 2x. Plus c. Well, friends, let's just try one definite integral, and then we'll go ahead and call it a day here. So we've kind of been able to kind of slow down a little bit here as we're getting closer to the end of the course, and as we're going through and looking at a bunch of different derivatives and integrals here. Let's try one definite integral, and then we'll call it. So, friends, why don't you guys go ahead and try this one right here. Go ahead and pause the video, and let's see how you guys deal with this. Go for it. All right, let's see how you did, friends. First up, if you needed to, feel free to use a u, just to make sure it works. If you do a u substitution, again, make sure that you change your bounds, but this is not one we needed to do a u substitution because everything equaled out. So we have 1 over the base, 1 over the natural log of the base, times 2x plus 3, 1 to 4. Now, friends, if it were me, I'll be honest, I'm going to pull out that 1 over natural log of 2. It's just a constant number. It doesn't need to be in there when I evaluate. So now we're dealing with 2 to the x plus 3. And now we can go ahead and evaluate it. It's 1 over the natural log of 2. 2 to the 7 minus 2 to the 4th. And if this is a FRQ, you'd stop there. If it's a multiple choice question, well, you'd go a little bit further here because you can. Oh, 2 to the 7th, that is going to be 128 minus 16. And you end up with, friends, 112 over the natural log of 2. All righty, friends. Well, that takes care of our exponents and logs. And we'll talk a little bit more about it tomorrow in class. So, guys, have a great rest of the day. Take care.